Good morning and welcome back. Today we will still use distance learning or online learning. I will upload our course material to YouTube so you can study at home. First, we will continue our discussion about localized radiation source. So, source is localized. What is the source? What is the radiating source? The source is charge source and current source. These two sources will generate radiations. So we will study a localized source, rho and J, current source and charge source. These two sources will generate phi and A, scalar potential and vector potential. So this equation is inhomogeneous because we have source term here. So the wave equation is inhomogeneous. And the solutions, what is the solution for this source? We can simplify into basic structure of inhomogeneous wave equations. Looks like this one. And we already discussed the solution of this one before, actually in chapter 6 and previous lecture. So you can check page 1 to page 10. Okay. So before we start, I will tell you what is this source come from. We say this is a prescribed source. That is, someone give you this source. But you should keep this in mind. This source comes from something like a oscillating source, sinusoidal oscillating source, or any other source. Okay. But at this point, we just omit the source, the origin of the source. Just imagine, just assume we have the source. In chapter 10, I will tell you this source come from the incident wave, come from synchrotron radiation in chapter 14. Okay, and this source also will be affected by E field and B field through Lorentz force. Okay, so that's about plasma physics. So now we just assume we have a localized oscillating source, rho and J. And rho and J can be static, can be alternating current source, or just static current source. The inhomogeneous wave equation looks like this one, and we know we just because of the causality, we just consider outgoing wave boundary condition. So no incoming wave, just outgoing wave. We have a localized source and the wave will propagating outside. So observer is far from the source. That's the most basic assumption. So we use outgoing wave boundary conditions. So phi becomes G plus for outgoing wave, xt, s prime, t primes. And this is the source. Perform volume integration and time integration. So where G, xt, x prime, t prime equals delta function, t prime minus t minus this one, separations, divided by x minus s prime, absolute value. So this is the G. Just imagine if this is static, time independent, so we don't need to consider this one. Then T, let it is static. So this one just like a delta function. After integration, this one give us exactly 1. So we just perform Volant integration. So green function becomes 1 over x minus x prime. That's for a static case, the simplest case. Okay. So the solution for this one, so green function, this is obtained from this one. Okay. This part just a review. Just a review. So maybe we should go back to page 1 to 10 and just go over the material again. Page 1 to 10. Page 1, we talk about in chapter 9, we have a prescribed source. We have a prescribed source and outgoing wave to the infinity. So boundary condition is simple. And then we start with source free. We source free and we use Fourier transform. So we just consider one Fourier components at one time. That's Helmholtz wave equation. This is the Helmholtz wave equation. Okay. With this one, we can perform separation of variable. We write in spherical coordinates. And separation of variable, we can separate into 3 parts: r dependent, theta dependent, and phi dependent. And r dependence, we have extra terms here. Theta dependence quite similar to the previous one. Phi dependent, very easy. So phi dependence just exponential im phi and exponential minus im phi. Theta dependent, we have associated Legendre polynomial. So these two are quite simple. We have learned this part already. And R dependence, we will have something new. R dependence, we have extra term k squared. So k squared will give us a new Bessel functions. So by substituting, we say this is FL. FL, just like UL. And then we will rewrite into 1 over R square root of R times UL, lowercase u. And that's the equations looks like. And solution for u will be Bessel function, but this time L is integer, but here is not integer, it's a fractional order. Bessel function, Newman functions. So FL, that is this term, that is this one, is actually 1 over square root R times J fractional order, 1 over square root R times N fractional order. So we can rewrite this one into this form. Lowercase j and lowercase n, okay? And we can combination of this one. Looks like Hankel functions, but this time, yeah, lowercase j and plus I n l and j l minus I n l, okay? So looks like sinusoidal cosine plus sine, cosine minus cosine plus I sine, cosine minus I sine. Similar. We will have a look at the behavior of these equations. So psi x omega becomes this one. This depends on R. This and YLM depends on theta and phi. Okay, good. Just a review. For the Laplace equation in cylindrical coordinate, we have similar result. And at that time, Laplace equation, we have Bessel function. For cylindrical coordinates, we have Bessel functions. And just a review. So the Bessel function looks like this one. Okay, very similar. But actually, we are talking about spherical coordinates. However, Bessel function and the Newman function just very similar to cylindrical coordinates. Okay, Hankel function, similar. So have a look at this one. J0, J1, J2, just like this one. And from here, it looks like sinusoidal, but a little bit exponential decay. Sinusoidal. And J0 is not to infinity, but J0 at x equals 0 here is actually 1. Okay? And N0, what will happen to N0? It might diverse. Okay? You can check Jackson, page 426 to 427 for further properties of the spherical Bessel function and spherical Hankel functions. So now, G is this one, okay? Because we consider time-independent equations. So the green function for G will be this one. And we can use spherical Bessel function and spherical Hankel functions to rewrite these equations. How to do that? We will use two properties and join together. We will separate into two parts and join together. So this is the final result. Go back to this one. We're equating the two expressions above for green functions, and eventually we obtain this one. Okay. With this one, we can calculate many things: electric dipole, magnetic dipole, electric quadrupole, and so on. Okay. So for Laplace equations in chapter 2, chapter 3, and at that time, our solution is simple. Our green function is simple, very simple. Okay. But now, with the Helmholtz wave equation, Helmholtz equations, and time-independent wave equations, we have these solutions. And the expansion, we have series expansion for the green function. And here, we have 1, equation 9.98. And once again, that's a comparison. Helmholtz wave equations, inhomogeneous, and wave equations, time-dependent, time-independent. Okay? The green function will be like this one. This one. That's the green function. And expansion. That's the green function. And yeah, no exact expression. Expansion of the green function. Okay, let's move on to the next page. So now we have the green functions. So the green function looks like this one, and we have source term, and after volume integration and time integration, we got A for J, 5 for rho. That's equation 6.48 and equation 9.2. In general, the sources, J, rho, contain static part and time-dependent part. So we will separate into, maybe we can separate into two parts, static part and time-independent part. Static and time-dependent, two parts. Let's consider static part. For static part, equation 9.2, with static A and phi, we got chapter 5 and chapter 1 respectively. Chapter 5, we got this one. And chapter 1, we got this one. That's for static part. Easy. Very simple. And time-dependent part. Time-dependent part we will consider. Let's use pointer. We have fields by harmonic sources, time-dependent sources. Only one time-dependent sources can only time-dependent sources can radiate. Time-independent sources, static part, can generate E field and can generate B field, but they cannot radiate. What does this mean? That means E field and B field will decay very quick. Okay. However, AC field, it will radiate. At very far, we can still receive the E field and B field. That's radiation. Radiation from moving charges are treated in chapter 13 and 14. Here we specialize two sources of the form. Simple sources, exponential minus I omega t, one harmonic component, one at a time. Okay, so overall, we separate into space dependence and time dependence. By doing so, we know this one will be phasor. So this is real. We should take the real part of this one. So this one contains amplitude and phase, contains vector and phase. So it's phasor. Now let's substituting equation 9.1 into 9.2, and we will carry out the T prime integration, and we will obtain these solutions. Still simple. Okay, still very simple. Carry out the T prime integration, and we got this one. And keep in mind, K equals is defined as omega over C. We should assume that Jx here is independent of Ax. That is, the source will not be affected by the fields they radiate. So in this case, source and field are independent. But later on, we will allow they have some correlations. That is, E field and B field will modulate the source, modulate rho and J through Lorentz force. J and A will generate fields through wave equations, and the new field will modulate the source. And the source will generate a new E field and B field. So they will become nonlinear feedback. So the system will be easily enter nonlinear behavior or even the chaotic behavior. So here we just assume they are independent. Just assume that. Okay? We can derive equation 9.3 using a simpler derivations. We study the harmonic source from the outset. Harmonic source from the outset. And we assume A is also harmonic. Keep this in mind. Real. So in fact, we should take the real part of this one. We should take the real part, RE, of this one. Phasor. Okay? Laplacian plus k squared times AX minus mu 0 JX. That's inhomogeneous Helmholtz wave equation. Without these terms, it's homogeneous Helmholtz wave equations. But with this term, it's inhomogeneous. So we know the green function for the above equation is this one. That is this one. So AX is simple, just green function times the source terms, mu 0 over 4 pi volume integration. Okay, so once again, we just move the coefficient mu 0 over 4 pi to the front and perform the volume integrations, which is exactly equation 9.3. Okay, so we can start from different derivations and we will have the same equations. Okay, what's next? What's next? We talk about static case. How about non-static? Okay, so our job is to find, okay, let's consider this one again. So we have vector potential A here. It's complex. We have complex term, complex. And Maxwell equation give us these relations because we discuss radiations. So normally we don't consider material. So under this assumption, the material property will be mu 0 and epsilon 0. It's just free space. Free space means vacuum. Just propagate in the space. In that case, B field equals curl of A. So H field equals 1 over mu 0 curl of A. That's everywhere outside the source. Yes, even close to the source, the same. And E field, because it's radiations, we can calculate with these relations. E equals curl of H. Okay? Because of the radiations. We obtain this one from page 297. Okay, objections. So Z0 is characteristic impedance. The dimension is exactly the same as ohm. Exactly the same for Z0. So we have Z0 here. We have K here. Okay. Let's equation 9.4 and equation 9.5. Okay, so interestingly, it looks like we should have not just vector potential, but scalar potential as well. But here, all we need is a vector potential. We don't have to consider the scalar potential because we don't need the scalar potential. I will show you in the next page why scalar potential is not needed. Actually, we already considered this one. I will show you in the next slide. Okay, this one is okay, no problem. Everybody can accept this idea easily. But this one is not that easy. So I will spend a lot of time. I will spend one page to show you how we obtain these equations. Okay, note that we have exponential minus I omega t dependence has been assumed for J. J is the current source. Hence, all other quantities which are expressed in terms of J. In terms of J only. The charge distribution rho and the scalar potential phi are not required to determine H and E. Interesting, right? Very interesting. Because all we need is H is J. Why? Because everything is connected. We have conservation of charge. So if we want to divergence J is related to partial rho, partial T. Okay, so we don't, actually rho is related to J. So phi will be related to J. So everything will be related to J. That's the idea. Okay. So now let me show you equation 9.5 is valid outside the source. Okay. Equation 9.5 is valid outside the source. Let's write this equation again. And we know H can be written into mu 0 times curl of A. And Z, just write it down. We have Z is mu 0 C squared divided by omega. Okay, go back to this page. Omega is K defined as omega over C. And Z is mu 0 over epsilon 0. And C is the speed of light. C squared equals 1 over epsilon 0, mu 0. So we just substitute everything to here, from here to here, okay? We have a mu 0, mu 0. So cancel out. So the result become IC squared over omega. And once again, we have a triple product. Curl of A. And this one becomes this one. Okay, becomes this one. And because of Lorentz gauge tells us divergence A equals minus 1 over C squared partial phi partial T. And phi also has exponential minus I omega T dependence. So minus minus we becomes I omega C squared phi. Okay. The phasor notations. Keep this in mind. Okay. Phi in the beginning has time dependent, but here just space dependence. So homogeneous wave equations becomes Laplacian A equals I omega equals this one. That's homogeneous wave equations. Outside the source. Outside the source, no source terms. Therefore, it's homogeneous wave equation. That's valid for outside the source. Therefore, Laplacian A equals I omega again times C squared. Actually, it's minus minus. Okay, but minus minus doesn't matter. So E becomes this one. IC squared over omega. IC squared over omega. And then this one becomes gradient I omega over C squared. Okay? And this one, the second term here, we have minus omega squared. Minus here. And I omega over C squared over A. We have C squared, and we have C squared here. C squared cancel out. Okay? omega, omega, omega. Once again, cancel out. And we have a minus I, so it becomes minus gradient phi, minus gradient phi, and this one minus I minus I omega. Okay, minus I omega. Omega, omega. We have I here, so give us a minus, and omega cancel. I omega. Okay, so we have 3I, I, 3I minus and another minus I. So we got this one. Then we can rewrite in terms of phasor equals to minus gradient phi minus I omega AX. Note that we have exponential minus I omega t dependence has been assumed for everything A, phi, E, H. If we consider time-dependent source, then we should consider, take this back. So EXT equals minus gradient phi minus partial A, partial T. So outside the source, we got this one, homogeneous wave equations. And outside the source, this one is equivalent to this one. Okay, let's feel better. So we know everything can be expressed in terms of J only. With J, we can calculate H. With H, we can calculate E. So outside the source, all we need is current source only. Okay, so let's move on to next page. Next page, we will consider, next 3 pages, we will consider actually 3 conditions. 3 conditions. First is near field, very close to the source. And second is intermediate field, intermediate. And the third is far field or far wrong. So we have near field, near wrong, intermediate wrong, and far wrong. And the most important part is near wrong and intermediate wrong. And near wrong will be very similar to static case. Because near field, we are very, very close to the source. Our response will be in phase with the source. So looks like static case. So near field, everything looks like static case. Let me show you. We have vector potential, mu 0 over 4 pi d3 volume integration, green functions, and Js. Before going to the algebraic details, we may readily observe some general properties of Ax near the source. Lambda is the wave, and R is the observer. For X outside the source, and we have this one will be very, very close. Very, very close. K is related to the wavelength. K is actually 2 pi over lambda. That's the wave number. Omega over C. We left exponential minus ik x minus s prime because near field, this will be very close to each other, close to 0. Very small compared with lambda. Okay, This one, so the here will be very, very small. Obviously, this one close to 1. And this one, just 1. We can expand the green function using 3.70. We talk about this one in page 10. You can go back to page 10. Okay? That's the series expansion. Since R is greater than R prime, always, because it's localized current source. The source is localized to a small region, and observer is outside the source, and outside but still near. Because of these terms, we know the larger R will be R, the smaller R will be R prime. So AX will be approximately under these conditions, under this assumption. So we will 4 pi YLM, 4 pi, this part the same. We just substitute 4 pi here. 4 pi cancel with 4 pi. So we got mu 0 here. And then sum over L, running from 0 to infinity, the same. Sum over M runs from minus L to L. 1 over 2 pi L plus 1. And 1 over R L plus L 1. YLM theta and phi. R theta phi independent of x prime coordinates. So only this one left here. And this one R prime left here. R prime to the L. And no others. So this is the terms to be integrated. The source terms. Source terms times R prime L YLM complex conjugate is function of theta prime and phi prime. The integral in 9.6 yields multiple coefficients as in 4.2. We will have multiple expansions. Obviously not today. Next time. So last equation 9.6 shows that for near field conditions, AX can be decomposed into multiple fields which fall off quickly as R minus L plus 1. This one. Fall off quickly, just as the static multiple fields. So actually this equation is quite similar to 4.2. Not similar, exactly the same. But the major difference is for real A time-dependent part, we still have exponential minus I omega t dependence. However, we will show later that far from the source, AS behaves as an outgoing spherical wave. So we just consider near field. Near field, the source terms is almost in phase with, because very close to the source. So looks like it's received the signal like steady case. That's why everything looks like static. Okay. But now let's consider a complete expansion or a full expansion of AX. Okay, let's face let's introduce our good friend, Bessel function, a green function. We may, in fact, expand AX without approximation. This time, no approximation at all, and we will use equation 9.98 again. For X outside the source, we have outside the source, So R larger is X equals R. R smaller equals X prime, absolute value, equals R prime. So outside the source, the green function can be write into this form. This part, the same. This part, we just write it down outside the source. That's R smaller. That's R larger. R larger. Okay. R smaller. So we know smaller j will be 0 when R prime equals 0. And HL will be 0 when R close to infinity. So these two product together to make sure close to the source, correct. Far from the source, correct. Everything is correct. Okay. So next step is substitute this one into here. So we got AX and perform the volume integrations. We got AX. We will obtain AX equals mu 0, the same. IK here. 4 pi will cancel out with 4 pi here. Sum over L and M. HL. First kind. Hankel function of the first kind. This one can move out from the integral. And YLM can move out from the integral. So inside just volume integration. JX from here and JL, spherical Bessel function from here, and spherical harmonics, okay, from here, okay. And just for your reference only, HL of the first kind can be expanded into this form, and the coefficient AN will be this one, okay. I do not expect you to remember everything because it's quite difficult. So you can stop here, but just keep in mind H can be explained into R dependence, okay, and RL plus 1, sum from 0 to 1. So this part will be never greater than RL. So obviously will be Hankel function of the first kind will be smaller than 1 over R, 1 over R squared, 1 over R cubed. So Hankel function will converge at very large R. Okay, and the coefficient is also finite coefficients. You can see the textbook, Handbook of Mathematical Functions. We will use these properties only. We don't want to derive from the very beginning. Okay. So equation 9.11 is an exact expression for vector potential, phasor part, AX. Now we assume K d smaller than 1. Okay, d. What is d? D is the dimension of the localized source. That means K is 1, 2 pi over lambda. It's the wave related to wavelength. And wavelength is much greater than the source dimension. Okay, let's assume this one. So spherical Bessel function can be rewrite into this one. Okay, simplify the expression. We will simplify the expression. This is always true, always true. Just imagine the localized source is just an angstrom. It's just an angstrom. And wavelength is normally much greater than the angstrom. Maybe a meter, a centimeter, a millimeter, or a micrometer, or a nanometer. This assumption is always true, always true. So spherical Bessel function can be simplified into this form. Go back to the previous page. Spherical Bessel function. No. Okay, I do not write here. You can go back to equation 9.88. 9.88. We will got these relations under these conditions. And substituting these relations, once again, go back. This one, okay? We just substitute this one. Okay. And equation 9.88 into equation 9.11. 9.11 is this one. So we got the form of this one under this assumption. And this one is still the same, no change. This one is simplified. Spherical Bessel functions can be simplified. Maybe we should go back to spherical Bessel function again to help you have a better understanding. Page 7. Let's go back to page 7. J is here. Okay. And J can be J here. Go back to page 18. Okay. Substitute everything into equation 9.11. And eventually we got AX. Okay. In terms of series expansion. But not finished yet. That's for J, spherical Bessel function. These terms. And we still have these terms. And once again, this term will become much easier to deal with. Okay? To be determined is still not ready yet. Equation 1 is the combination of equation 9.6 and 9.12 in Jackson. It's valid for KD smaller than 1 and any X outside the source. The region outside the source is commonly divided into 3 zones. First is near zone. That is, the source is always localized. So that's why we say a localized oscillating source. So D small. And R is observer. Lambda is the wavelength. If R is somewhere between D and lambda, then we say it's near wrong. If R is approximately equals to lambda, we say it's intermediate wrong or induction wrong. And R very far from lambda and D, then is far wrong or radiation wrong. So we will divide it into static wrong, induction wrong, and radiation wrong. Intermediate wrong or induction wrong are it's difficult to understand. So we don't want to spend too much time here. We will focus on near wrong and far wrong. And near wrong is easy, just like static case. So we already discussed the static case before. So we will focus on far wrong, based on this one, So next time we will talk about, we got A, and then we will calculate H field. With H field, we can calculate E field. With E and H, we got everything. We don't need to discuss scalar potential. Vector potential is sufficient. Okay, but we still have time. What should we do? I will remind you with Griffiths. Griffiths chapter 11, we talk about dipole radiations. So in the next 6 pages, we will discuss about the dipole radiations. Let's consider we have two charges, minus Q and plus Q. These two charges will move sinusoidally, Q from here to here, and minus Q from here to here. So we will have an oscillating electric dipole. So P is the charge times the separation, T. And this separation will become, it's a vector. It depends on time, sinusoidal. So separate into, this one is in G direction. And if minus Q move to here and plus Q move here, we will have minus Z directions. Okay, so absolute value, the magnitude of P0 is QD. Okay, so retarded potential will be easy. Separation here, the source here, first source, second source, and we can calculate vector potential. At that time, we separate. In Jackson chapter 9, I just told you that vector potential is sufficient. But in Griffiths, we still consider V, and V is the scalar potential, and A is the vector potential. So scalar potential V, easy, source, volume integration, and T are attack times from here to here. Observer is here. Observer obviously will be much larger than this one. Okay, that's the dimension D. Okay, Q0 here. Actually it's Q. Cosine omega, actually, yeah, it's Q. It's Q, not Q0. That's typo. Cosine omega t times, it takes times to propagate from here to here. The time is gamma separation plus divided by C. Propagate from here to here takes times. So observe here is a little before. And R plus is the separation. R minus is another separation. Because charge plus and charge minus, so we have a minus sign. And then we will have first approximation. Approximation number 1, make this physical dipole into a perfect dipole, d smaller than 1, outside the source. And outside the source, we can rewrite, simplify this one into here. R separation into this one separation. So 1 over R plus and minus becomes this one. So cosine terms can be rewrite into cosine with this one and this one. So we can write into cosine times another cosine. Cosine this term and cosine this term. Minus and plus sine this term, sine this term. Okay. Second approximation is d is very smaller than lambda. Lambda. Omega over c. Omega over c. So d is smaller than lambda. D is the physical dimension of the radiation source. R is outside the source. Lambda should be larger than the source. Okay? That's second approximation. With this approximation, we got these terms. This term will be small, very small, very small. So you can consider this one very small, so equals 1. And this one very small, so equals this one. So we got this equation and equals 1. Equals cosine omega t minus r over c times 1. Good. And minus plus sine omega t minus r over c. Omega d over 2c cosine theta. Okay? So the retarded scalar potential is here. VR is RT 1 over 4 pi epsilon naught. Cosine this one, sine this one, and exponential, and these terms. This one times this one. Go back to this one. We expand this one, as well as gamma plus and minus. Gamma plus and minus becomes here. Okay, and cosine this one becomes here. Okay, so we have this term times this one, and this term times this one. Okay, after simple calculations, we can rewrite into this one. Okay, P0 cosine theta minus omega over c, omega t minus r, the same. And this one, this one is still survive. And another one is cosine. Okay. It's not finished yet. We need a third approximation. At the radiation wrong, that is far wrong, far field, observer is much larger than the wavelength of the wave. So its retarded scalar potential becomes this one. Okay, so eventually we got a very simple scalar potential. P0 cosine theta over 4 pi epsilon 0 times r minus omega over c sine omega t minus r over c because of the three approximation. That's the first approximation. Dipole is localized, so dipole should be small, and observer should be outside the source. Dipole should be small, and wavelength should be larger than the source. And last one, wavelength should be smaller than observer. So we have this assumption. This assumption is exactly the same as Jackson's assumption for the far field. So Griffiths and Jackson use the same assumption. It's not finished yet. We still have vector potential. The vector potential, retarded vector potential. Retarded vector potential is determined by current density. IT is dq over dt. Q will move in this one. Okay? So it's minus Q0 times omega sine omega t. Because the charge move up and down. Charge move up and down. So current becomes sinusoidal. Okay? And with this current source, we can calculate vector potential. Vector potential, retarded vector potential. And once again, we use the I change to J separation and perform time integration. D from D minus D over 2 minus D over 2 to plus D over 2 minus Q omega sine omega t. That's the retarded time. Okay, under this three assumption, far field, far wrong, radiation wrong assumption, we got A. We got A. That's the vector potential. Vector potential equals minus mu 0 P0 omega divided by 4 pi r times sine omega t minus r over c. R is here. R over c is here. Okay, in the z direction. So vector potential is in the z direction. Scalar potential is a scalar. It's not a vector. Okay, so retarded potential becomes here. This retarded scalar potential. Retarded scalar potential. And E equals minus gradient phi V minus partial A partial T. And B equals curl of A. That's for Griffiths. One more pages. So the electromagnetic fields and Poynting vectors. Now with these two scalar potential and vector potential, we can calculate E. Okay, very easy. And with B, we can calculate. With A, we can calculate vector potential. Mu 0 over P0 omega squared divided by 4 pi C sine theta over R cosine theta. Okay, so we have E, we have B, we can calculate Poynting vector. Okay, so Poynting vector will becomes in the R directions. R direction. The total power radiation will be Poynting vector integrate over all the surface will be mu 0 P0 squared omega to the fourth divided by 12 pi C. That's the total power radiated. So it will proportional to frequency to the force and dipole moment. And look at this case, Poynting vector. Poynting vector is power per unit area. So from these viewpoints, sine theta, when theta equals 0, theta equals 0, theta equals 0 here. This is the z direction. Theta is the angle between the z-axis. So theta equals 0 is here. No radiation at all. Theta equals pi over 2 here. Sy plane. Then sine pi over 2 equals 1. We have the largest. So radiation in this region will become largest. Sy plane will become largest. And the z-axis will be 0. Okay, that's the major difference. That's good for dipole radiation, especially electric dipole. That's for electric dipole. Okay, so you can see here, Griffith starts from the simplest case. It considers vector potential and scalar potential only. However, Jackson just consider vector potential. So Jackson's material is advanced a little bit. It just consider current source. With the current source, we can calculate scalar vector potential. With the vector potential, we can calculate H field, and we can calculate E field from the H field. Okay. So you can compare. If you don't understand, you have no idea about. If you are not familiar with Griffiths, I will strongly recommend you to study Griffiths again. Study chapter 11 again. Will help you a lot. Okay. If you have some idea about Griffiths, then you will have a solid ground, and you can study Jackson much with good background, much easier for you to understand. Okay, so let's go back to here, maybe here or here. With J here, we can calculate A. With A, we can calculate H. With H, we can calculate E. With E and H, we can calculate pointing vector. So everything all starts from the source functions. So next time, we will consider J terms only. So I will briefly introduce our job next time. Electric dipole fields. We can calculate A from current source and consider L terms. We got the simplest terms, A. So A is actually related to dipole terms. So with this one, we can calculate everything. We can calculate H, we can calculate E. Okay? That's the complete equations. And for the far wrong, we can simplify this equation again. Okay? For the near wrong is different. Okay? For the near wrong, E field and H field are out of phase. And for the far wrong, they are in phase. They can radiate. That's very interesting. And we can calculate the pointing vectors per solid angle. So it's different. The time average power in the far wrong per unit solid angle. So it's not exactly the vector, the pointing vector. It's still times this one, r squared. Okay. And then we will consider higher order term L equals 1. L equals 1, we will consider M equals minus 1, 0, and 1. And then we got another terms, magnetic dipole and electric quadrupole. So we got two terms. The first term will be related to electric quadrupole. Second term is magnetic dipole radiation. So eventually, we got Hn and En from these two terms, okay? And we still have divided into far wrong here and near wrong here. Near wrong is once again out of phase, so average power is 0. Far wrong, of course, in phase, so average power is not 0 at all. PT will be here. So it's comparison between static and time-dependent cases. Static case, okay, that's static case. Time-dependent case, we start from here. Okay, and we have some corrections for this one. And how to excite electric dipole and magnetic dipole. Here is a simple example. If we have H field inside a waveguide and we have a small coupling, so the field will distort and leak outside, and outside will have a equivalent to a magnetic dipole outside, and we have magnetic dipole inside. So outside is a dipole radiation. And another case, we have E field perpendicular to this plane, and we have a small opening. Then it looks like outside. Looks like we have a dipole outside. Okay. This one published in 1944 in Physical Review by Hans Bethe. Theory of diffraction by small holes, and he won the Nobel Prize in 1967. Okay, next time we will talk about up to page 35. Okay, if no other questions, you can come to my room office. The office hour is the same as before. So the room office number I already give you through the IMSL. So you can log in to the room meeting room, okay, and discuss your question with me. Okay. If no other question, I will stop here. See you next time.